Welcome back to lesson U2A7, where we're discussing the intersections made between two planes. In this case, we're using their normals to determine the number of possible solutions and how the two planes are positioned against each other. So in this case, we are given the equations, a scalar form of the equations of two planes, which we will call planes pi1 and pi2. We'll start off by identifying their normals. Recall that the normal to a plane is determined by the values of the coefficients of x, y, and z. So we'll have 2, -1, +3 for the first plane. The normal n2 for plane pi2 will be, as you can see, for x we have the coordinate 1 or coefficient 1, which makes coordinate 1 for the normal. And as you can see here, we are missing the value of y, so we're missing the y term. So missing the y term means that the term y must have had a coefficient of 0. So this will give the normal the y coordinate of 0. The z coordinate will be -3. As you can see here, these two normals are not scalar multiples of each other. So we'll say that n1 is different than kn2. And when normals are not scalar multiples of each other, it means that the two planes will intersect along a line. Which means that we can move on with the next step in the process to determining the equation of the line of intersection. Now, let's start solving. Remember that in this for previous examples, when we solve for the equation of the line, we try to bring or to create an equation that describes the relationship between two variables in the system. And as you can see here in our case, the second equation describes the relationship between two variables in this system, which means that we do not have to go through the elimination process we had to go through in example number 3. For this, you look at video number 2 of lesson U2A7 Part 1, which means that we can start right away to finding the equation of the line. So that would be our step number 1. So we'll start off with x minus 3z equals 1, and let z be some scalar. Remember that you can, and I'm going to choose t, you can choose either x or z to be given a scalar value. So if z equals t, which means that I've just created the first parametric equation for the line of intersection, then x minus 3z equals 1 will change to become x minus 3t equals 1, which will make x equal to 1 plus 3t. So this will be the parametric equation for the x coordinate. In the next step, step 2, we will try to find the parametric equation for the third variable, the variable y. And the variable y appears only in the first equation, so we have no choice but use equation 1 for pi1 to determine y. So find the parametric equation for y, which is the parametric equation of the third and last variable that we're trying to find. So we have 2x minus y plus 3z equals -2. I just wrote the equation as is first. Now for x, now we have 1 plus 3t minus y, which we're about to find, plus 3z, so for z we have t, equals -2. Again, all we have done in here is replace the x coordinate by its parametric equation and replace the z coordinate by its parametric equation. Let's solve for y. We have 2 plus 6t minus y plus 3t equals -2. Negative y would equal negative 2 minus 2, so we're taking 2 to the other side and change the sign, and 6t plus 3t, which makes 90, will come to the other side as negative 90. So we'll have negative y equals negative 4 minus 9t, or simply y equals 4 plus 9t. And this will be the third parametric equation for the line of intersection. So as you can see here, we have the parametric equation for x, which is 1 plus 3t, the parametric equation for y, which is 4 plus 9t, and for z, which is just z equals t, we're going to write 0 plus 1t. So therefore, the equation of the line of intersection is x, y, z equals, so we're going to start off with a starting point, which is all these constants together, 1, 4, 0, plus some scalar t, and then the coordinates of the direction vector, which are determined by the coefficient of the scalar, in our case 3, 9, and 1. And voila, this would be the vector form of the equation of the line of intersection. Now let's take a look at our last example for this lesson, example 5, selecting a strategy to solve a problem involving two planes. In this case, we have to determine the equation of a line that passes through some point with coordinates 5, negative 2, 3, we call this a point P, and is parallel to the line of intersection of the plane pi 1 and pi 2. So the equations of each plane are given in Cartesian form. So as you can see here, we have two planes, pi 1 and pi 2, and they will intersect along the line of intersection. Now the line of intersection will have a direction vector m. We need to find the equation of a line that is outside these planes. So a line drawn from point P, which is right here, and is parallel to this line, which means that they must have the same direction vector, or their direction vectors must be scalar multiples of each other. So in order to determine the equation of this line, because that's what we're trying to find, then we're going to say that the line L1 that we're about to find will have the equation in vector form xyz equals the starting point, and it only makes sense that for starting point we use the coordinates of point P, 5, negative 2, and 3, plus some scalar, and then the coordinates of the direction vector, which we are about to find. And for now, we're going to call them by letters A, B, and C. Now, providing that the line L1 will be parallel to the line of intersection, it would be useful to find the direction vector of the line of intersection. So we're going to call L2 the line of intersection of two planes. Between pi 1 and pi 2. So our job now will be to find the equation of the line of intersection, which means that we have to put the two equations together in a system. So we'll have x plus 2y minus z equals 6. And for pi 2, we have y plus 2z equals 1. So it seems that we are missing the x-coordinate, which tells us that the x-coordinate must have had a coefficient of 0. So the normal n1 for plane pi 1 will be 1, 2, and negative 1. And the normal n2 for plane pi 2 will be 0, 1, and 2. As you can see, there is no relation between n1 and n2, so they're not scalar multiples of each other. And the coordinate that gives it away right away is the coordinate 0 here. So therefore, the lines intersect. the planes pi 1 and pi 2 will intersect, so it's for sure, along a line L2, which I'll call it the line of intersection. So let's find out the line of intersection. Now, as you can see in here, we have the second equation that describes the relationship between two variables. And when we solve such systems of equations, that's what we want to create first, and this is given in this case. So we'll use this equation. That would be our step number 1, if you remember from the previous examples. So we're going to use the equation that describes the relationship between only 2 out of the 3 variables to start creating the equation of the line. So we're going to let z be some scalar t. And then find an equation, a parametric equation for y. So y plus 2z equals 1 will become y plus 2t equals 1. So that will make y equal to 1 minus 2t. So far we have created 2 parametric equations, one for z and one for y. In the next step, step number 2, we'll find the parametric equation for the third variable, which in our case will be the variable x. And for this, we have only one choice. We have the equation 1 to solve for x, because that's the only equation where x makes an appearance. So we have x plus 2 instead of y. We'll write the parametric 1 minus 2t, as you can see here. And then instead of z, we'll write the parametric for z, which is just t. And now let's solve for x. We have x plus 2 minus 4t minus t equals 6. X equals, take 2 to the other side, so that means 6 minus 2 is 4. And negative 4t minus t is negative 5t. When you take it to the other side, we'll make positive 5t. And now we have the parametric equation for the third variable. So therefore, we're going to say that the line of intersection L2 will have the equation x, y, z equals a starting point. So for x we have 4. For y we have 1. And for z we have 0. So I have a constant of 0 there. And then plus t. And then for the x coordinate of the direction vector, we have 5. The y coordinate of the direction vector is negative 2. And the z coordinate for the direction vector is 1. So we'll say that the direction vector for line L2 will be m2 equals 5, negative 2, 1. And this direction vector can perfectly fit the direction vector of the line that is drawn from this particular point. So we're going to say that, therefore, the line L1 will have the equation x, y, z equals, so recall that line L1 has a starting point 5, negative 2, 3. Plus some scalar, I'm going to use letter S in this case, the direction vector 5, negative 2, 1. Remember that this is a possible line or equation of a line because for the direction vector we can take any multiple of 5, negative 2, 1, direction vector 5, negative 2, 1. So this would be the equation of the line L2, which is drawn from some point outside of these two planes and is parallel to their line of intersection. I hope this made sense and I hope you found the instructions useful. Thank you for watching and have a wonderful day. Bye for now.